And today it is a very special meeting of our seminar. Today we have several young speakers and session named by Skorokhod readings. And it is non-random that we have two these features, young speakers and Skorokhod readings. Because in my opinion, one of the main features of good mathematical talk is in some sense uncertainty, unpredictable of the results which we see in the talk. And it was one of features of Skorokhod. His talk always give you experience of something new, new facts, new proofs. They were always unpredictable. Young person also have this property because we don't know them at all. So it is their first attempt to do mathematics, to present mathematics. And from this point of view, they are also unpredictable for us. Today we will discuss different talks, and also we have to mention supervisors who managed master students, because it is also tradition in our department, which was created by Skorokhod. He always have a lot of students, a lot of persons with which he worked in very different direction in probability theory and stochastic processes. So it is a big pleasure for me to open this conference, and this mini conference is not the first one, maybe a fourth. So this became to be a tradition for our seminar. So I wish success to every participant, and we begin with the talk of Tatyana Kotelnikova. Valeriya Kotelnikova, a functional limit theorem for nested Karlin occupancy scheme generated by discrete Weibull-like distribution. Supervisor, Oleksandr Iksanov. So, Valeriya, please, you can demonstrate your screen.
Hello, everybody. I'm grateful for the opportunity to talk here today about my recent joint work with Oleksandr Iksanov and Zakhar Kablutchko, in which we investigated a functional limit theorem for nested Karlin's occupancy scheme generated by discrete Weibull-like distributions. Before presenting our main results, I will explain you about nested Karlin's occupancy scheme. And this scheme is, in a way, a generalization of infinite occupancy scheme. So we will start from it. Infinite occupancy scheme, or as it also known, classical Karlin's occupancy scheme. We have an infinite array of boxes with numbers 1, 2, 3, and so on, and we throw balls into these boxes with probability P1 of hitting box 1, P2 of hitting box 2, and so on. Here, pk is a discrete probability distribution. That is, all pk's are non-negative and their sum equals to 1. Additionally, we assume that there are infinitely many positive pk's. That means that ball can fall with positive probability into one of the infinite set of boxes. And at time n, we throw these balls. So we throw balls in the discrete time. Let's look at some example. Now it's time 0, so there are no balls. Then at time 1, a new ball arrives and falls for example, into the box 100. At time 2, the second ball arrives and falls, for instance, into the box 2. Then at time 3, it can fall into the box 3, at time 4 into the box 100, and at time 5, for instance, into the box 2. This is one of the possible realizations of these processes. The most important characteristics of this scheme when n balls have been thrown are the index of last occupied box Mn, the number of occupied boxes Kn, and the number of empty boxes within the occupancy range Ln, which equals the difference between Mn and Kn. In our example, the index is 5 because there were 5 balls being thrown. The index of last occupied box is 100. The number of occupied boxes is equal to 3. These boxes are 2, 3, and 100. And the occupancy range is the area between the first box to the last occupied box. So the number of empty boxes within this occupancy range equals the difference between 100 and 3. So it's 97. Also, we can represent these random variables Mn, Kn, and Ln in another way. Let Xi1 and so on Xn be independent random variables with distribution pk. In an informal way, Xi1 shows us in which the ball with number 1, in which box the ball with number 1 fell. Xi2 shows us in which box the ball with number 2 fell, and so on. So Mn is the maximum of the occupied boxes, and Kn is the number of distinct values of these occupied boxes. So with the number of distinct values between Xi1 and so on Xn. This version is called deterministic version, but there is another version of this infinite occupancy scheme, which is called Poissonized. Denoted by pi of t, a Poisson process on non-negative half-line of unit intensity, and denoted by S1, S2, and so on, its rival times. That is, pi of t is the counting process for the sequence Sn. In the Poissonized version of this scheme, the nth ball is thrown at time Sn, in contrast to the deterministic version, where the nth ball is thrown at time n. As a conclusion, in the Poissonized version, at time t, there are pi of t balls thrown. Why Poissonized scheme is also used? Denoted by pk of t, the number of balls which fall into the box k in the Poissonized scheme. So we can calculate that the number of all balls that have been thrown, pi of t, equals the sum of the number of balls which fall into different boxes. By the thinning property of Poisson process, pi1 of t, pi2 of t, and so on, are independent Poisson processes of intensities p1, p2, and so on, respectively. So, in the Poissonized version, the number of balls falling into different boxes, which we denoted as pk of t, are independent by the thinning property. In contrast to the deterministic version, where you can check that the number of balls falling into different boxes are dependent. This makes the work with this scheme more convenient because, for example, if we look at the random variable Kn, the number of occupied boxes, we can represent it in the Poissonized scheme as the sum of indicators depending on pk of t. And as we can represent this variable as the sum of independent indicators, we can calculate, for example, variance in more convenient way. So this explains the common approach which is used in works which deal with infinite occupancy scheme. The first scheme is Poissonized, so we replace n with pi of t. Then we solve the problem for the Poissonized scheme, and then the scheme is depoissonized. So we return from pi of t to n. This scheme was investigated by many contributors. You can see an incomplete list of them here, and I want to make some comments about some of these works. This scheme was at first investigated by Karlin in 1967, and the another name of this scheme is classical Karlin's occupancy scheme. So, as you can see, the scheme is named after him. Then, in 1989, Prykhodko proved a one-dimensional central limit theorem. This theorem states that the number of occupied boxes Kn, centered by its mean and normalized by its variance, by the root of its variance, converges in the distribution to standard normal distribution, under the assumption that variance of Kn diverges to infinity. You can read about the most significant results of this era up to 2007 in a survey by Gnedin, Hansen, and Pittman. In 2016, Chebunin and Kovalevsky proved a functional limit theorem on the assumption that pk is regularly varying at infinity. We also proved a functional limit theorem, but on the assumption that pk is slowly varying at infinity. And as far as we know, such functional limit theorem haven't been proved. Now we are ready to talk about nested Karlin's occupancy scheme. Let us denote by pk a discrete probability distribution. At first, we have an ancestor, or as it's also called, a root, with weight 1, and it constitutes the zero generation. Then this ancestor produces an infinite number of offsprings with numbers 1, 2, 3, and so on. And the weights of these offsprings are P1, P2, P3, and so on. These offsprings constitute the first generation. If we interpret individuals of the first generation as boxes and throw some balls into them with probability P1 of hitting box 1, P2 of hitting box 2, and so on, we will have Karlin's occupancy scheme generated by a probability distribution pk. Then, an individual k1 of the first generation with weight pk1 produces an infinite number of offsprings with numbers k1, k2. And it is postulated that the weight of this offspring equals the product of pk1 and pk2. All of the offsprings of the individuals of the first generation constitute the second generation. We can calculate that the sum of weights of the individuals of the second generation is equal to 1. So we conclude that pk1, k2 is a discrete probability distribution. If we forget the first generation and interpret individuals as boxes, interpret individuals of the second generation as boxes, and throw some balls into them with probability pk1, k2 of hitting box k1, k2, we will have classical Karlin's occupancy scheme generated by probability distribution pk1, k2. Other generations are formed in a similar way. The weight of kn plus first child of some individual kn and so, k1 and so on kn is equal to the product of pk1 and so on kn and pkn plus 1. In such a way, we constructed a tree of a weighted branching process with deterministic weights. It's rather unusual because normally the weights are random. What happens in nested Karlin's occupancy scheme? At time 0, infinite many balls are collected in the root, or as it's also called in their ancestor. Then, in the deterministic scheme, at time n, or in the Poissonized scheme at time Sn, I recall that Sn is the arrival time of Poisson process. One of the balls collected in the root arrives and falls independently of the previous balls into the box k1 of the first generation with probability pk1, And at the same moment, into the box K1, K2 of the second generation with probability pk2, into the box K1, K2, K3 of the third generation with probability pk3, and so on indefinitely. A box is deemed occupied if it was hit by a ball on its way over the generations. Let's look at some example. Let's consider the deterministic scheme. At time 0, infinitely many balls are collected here in the ancestor. Then at time 1, a new ball from this ancestor arrives and falls into one of the boxes of the first generation. For example, into the box with number 3. Then at the same moment, this ball falls into one of the offsprings of this third box of the second generation. For example, into the box with number 3-1. Then at this moment, this ball falls into the offspring of the box with number 3-1 of the third generation, and this repeats indefinitely. Nested Karlin's occupancy scheme was first investigated in our work, but there is a similar scheme, nested occupancy scheme in random environment. The difference between these two schemes are that in the second scheme, probabilities pk are random, in contrast to our scheme, where these probabilities pk are deterministic. Nested occupancy scheme in random environment was first investigated by Jean Bervan in 2008, and then was researched by such contributors, as you can see in the slide. Let us compare nested Karlin's occupancy scheme and nested occupancy scheme in random environment. Nested Karlin's occupancy scheme has the randomness of sampling. It means that this randomness means the randomness of choosing a box into which ball falls. In contrast to the nested occupancy scheme in random environment, where there are two randomness, the randomness of sampling and the randomness of probabilities. But the properties or the behavior of this scheme is determined by the randomness of probabilities. So the properties of these two schemes should be different. To look at our main results, we need some notation. Denoted by pk, as usual, a discrete probability distribution. Also, we shall consider counting function for the sequence 1 over pk, which is defined in such way for positive axis. The random variable with which we work is the number of occupied boxes in the jth generation when n balls have been thrown. And also we will consider for negative t and integer j such random functional. Our main result is assume that for all positive lambdas, condition 1 holds for some non-negative beta and some slowly varying at infinity function L. If beta is 0, we additionally assume that L is eventually non-decreasing and unbounded. Then we prove that Kj of t converges to the vector process Zj as t tends to infinity in the product J1 topology on Dn. Here D is a Skorokhod space, and Z1, Z2, and so on are independent copies of centered stationary Gaussian process Z with covariance function, which you can see in Formula 2. Let me make some comments about condition 1. The denominator here is a slowly varying function. If we replace this exact form of slowly varying function by arbitrary slowly varying function L of t, we will have the definition that function rho belongs to the Dehaene class pi. And it's known that every function which belongs to the Dehaene class pi is slowly varying. So we conclude that the counting function rho which satisfies 1 is slowly varying. What is the range of applicability of our theorem? We provided sufficient conditions under which given probability distribution pk's satisfies condition 1. But these conditions are too technical to represent them here, so I will discuss it in an informal way. Let's consider discrete Weibull probability distribution. So the case has such values where alpha is positive parameter and c is the normalizing constant, which guarantees that the sum of pk's equals 1. We can find by direct calculation the counting function rho of t. It equals an integer part of such logarithm in power 1 over alpha. At first, let us assume that alpha is from 0 to 1. Then condition 1 holds for such positive value of parameter beta and slowly varying function L of t, which is constant. So condition 1 holds in this case, and we state that functional limit theorem also holds. Now let us assume that alpha is 1. In this case, pk is a geometric distribution, and we can also calculate the counting function rho of t. We can check that the function in the numerator of in formula 1 is a bounded function which does not converge. On the other hand, if the denominator tends to infinity, this limit equals 0. So we conclude that condition 1 doesn't hold for geometric distribution, and we can informally conclude that our assumption 1 holds for discrete probability distributions, which decreases not so fast as geometric distribution. Let us consider for integer j and positive x, function rho j of x is the counting function in the gist level, which is defined in such way. If we put j equals 1, we will have the counting function rho, about which we spoke earlier, and which figurates in the our assumption 1. Then we can check that rho j is the j-fold Mellin-Stieltjes convolution of rho with itself. That is, such relation holds. For our proofs, we need to ensure that rho j belongs to the Dehaene class pi. I recall that our assumption of the theorem is that rho belongs to the Dehaene class pi. And there is an open problem. Assume that function belongs to the Dehaene class pi. Is it true that its Mellin-Stieltjes convolutions belong to this Dehaene class pi? This problem is open, so we needed to prove such lemma. The main aim of it was to show that rho j belongs to the Dehaene class pi. And this is the only place in our proof in which we needed the specific form of the denominator. For instance, if we want to state that functional limit theorem holds for the first level, so if we want to state that k1 of t converges to the z1, we do not need the exact form of the denominator here. We can replace it by the arbitrary slowly varying function L of t, and our functional limit theorem will hold. Now I want to say some words about the idea of proof of this theorem. At first step, we personalize the scheme. So we replace n with pi of t. Here, pi of t is the Poisson process on 0 infinity of unit intensity. And for integer j, we consider p, k1, and so on, kj of t, which shows us the number of balls which fall into the box with number k1 and so on, kj. This box is situated in the gist level. So if we want to find the number of all balls, pi of t, we need to sum the number of balls which fall into different boxes of the fixed level. So we have such relation. By the thinning property of Poisson process, the summands in this formula are independent, and they are Poisson processes of intensity pk1 and so on kj. We work with the random variable k pi of tj, which shows us the number of occupied boxes. A box is occupied if the number of balls which fall into it is greater or equal than 1. So we can represent this random variable as the sum of such indicators. And it's important that it's the sum of independent indicators, so we can, in more convenient way, find, for instance, the variance of this variable. At the next step, we prove weak convergence of finite dimensional distributions. We use Kramer-Bolt device to work with no finite dimensional vectors, to work with linear combinations of their coordinates. And to prove that this linear combination converges to normal distribution, we checked the conditions of the Lindeberg-Feller central limit theorem. At the next step, we proved tightness in the Skorokhod space D. We did this checking Billingsley's sufficient conditions in terms of moments. You can see the exact form of these conditions as the slide. And also we checked the sufficient conditions for tightness in the space of continuous span, but these conditions do not hold. After proving a weak convergence of finite dimensional distribution and checking tightness, we conclude that weak convergence in the function space also holds. And the last step that we need is to depoisonize our scheme with the help of the continuous mapping theorem. Now we know that the limit process Z is centered stationary Gaussian process, and we know the covariance function of it. But this information is inconvenient for the simulation purposes. So we provided an integral representation which gives us the pathwise description of this process. You can see this integral representation at the slide. Here the integrand is the random function, and the integrator is two-dimensional white noise whose intensity measure is a standard Lebesgue measure. So then we proved that if Z has such integral representation, that Z is exactly our central limit process with exactly the same covariance function. And moreover, using Kolmogorov-Chentzov theorem, we proved that process Z has a version with sample paths which are Hölder continuous with exponent alpha for every alpha from 0 to 1/2. It was a great pleasure for me to tell about our recent results. Thank you for your attention.
Okay, thank you very much, Valeriya. Maybe somebody have questions or comments, please. Valeriya, let me ask you, you already have a theorem about the number of occupied boxes. What about the distribution of balls through these boxes? So maybe if you can normalize suitably the number or size of occupied places, then we can expect that the mass of balls in these boxes under suitable normalization will go to some measure-valued processes. What do you think?
Can you repeat the question slowly?
Actually, I think that I even can draw the picture. So you see, you just proved that if we have this rows and take here the number of occupied boxes, then a number of these boxes, for number of these boxes, you have some limit theorems. Yeah, but let's normalize the size And maybe the weight in a sense that you have here a distribution, mass distribution. And maybe under the suitable normalization, you can get weak conversions to some measure valued process, mu t, where mu under fixed t will be a limit of the mass distribution at time t or something. Yeah.
What do you mean when you say size?
You introduced these characteristics, which is one is the maximum of psi n, yes. So this maximum is the size, yeah.
Yeah, okay, it's the length of the occupancy range.
Yes, exactly.
Okay. And you propose to normalize this Mn by the weight. You said to normalize by the weight. What do you mean saying weight?
Oh, you see, you have at the time n, you have weight n. Yes, it goes to infinity, but maybe in order to have some measure valued processes with good structure, we can normalize it like up to 1, for example, divided by n, by the number of balls or something. I don't know.
So I want to understand that I understood you right. You propose me to normalize the number of occupied boxes by the length of the occupancy range.
Okay, yes. For example, by n, you will get a random probability measure, yes?
Yes.
And maybe when we shrink the size, this mn, then one can expect that this random measure valued process will have a weak limit.
You propose to change the process kj of t, which we considered here.
This is just number. Yes, I just want to construct a measure on the real line related to your process. You can make scaling of space when you will just say that distance between boxes tends to 0. This distance, because now we can identify boxes with integer values, but then one can think about the distance like 1 over n, for example, or something. And then also normalize the number of balls. Then maybe we will have a random measure, yes, and maybe one can expect that this random measures will converge the suitable time scaling. Yeah.
Maybe. I will think about it. No, I will try to realize your idea. Now I don't know the answer.
Okay, thank you very much again. And maybe somebody else have questions?
Let me say a few words. Of course, your question makes sense, and actually, Professor Dorogovtsev is asking what the asymptotic behavior of the positions of occupied boxes as time becomes large. So we have random indices. So we have thrown some balls, and they occupied in some way our array of boxes, right? And now we look at the random indices of occupied boxes, and the question is what we obtain in the limit. I think at this stage, the correct answer is I don't know. This has never been investigated, but the question is very interesting and important, and we will do our best to explore this Yeah, but this is absolutely different problem from what we have done so far. Yeah, but of course it's very interesting. Yes, I agree.
Okay, thank you very much. But your theme reminds me some organization of super processes like Regina process, when we have just every particle have two gives two new particles or so on. So I think that maybe some bridge can be built.
Yeah, I'm sure you're right. I'm sure, but we didn't look into this problem so far. So, but
Okay.
it's very likely that there is some weak limits for this configuration.
Mhm. Okay, thank you very much, Valeria, again. And now we have to switch to next talk. And next talk will be talk of Oleksandr Prykhodko, which is named Limit Behavior of Random Walks with Reflection. Supervisor Andrey Pilipenko. Oleksandr, please start your talk.
Hello. So thank you for inviting me. So the topic of my talk is limit behavior of random walks with reflection. My name is Oleksandr Prykhodko, and this is a joint research with Oleksandr Iksanov and Andrey Pilipenko. I will start with the model. The model is as follows. I have a random walk tilde S. It has different distributions of above and below zero. Above zero, it is a sum of xi's, and below zero, it sums up etas. The xi's are mean zero and with finite variance. I will assume that the variance is 1, and etas are positive. The problem is to establish the convergence of sequences of tilde S in Skorokhod space when the scaling is as in Donskoy's theorem. So we multiply by n in time and divide by a square root in space. Yeah, this is the picture of this process. It jumps. So you see blue flat lines where the process is, and these red vertical lines are the jumps from below zero. These are etas. They are positive and happen when the process comes in the region below zero. I don't have much to say about motivation. I have purely mathematical motivation, but still there are some examples that you might find interesting. So the first one is evaporation of gas from liquid. It has been researched in physics. The earliest research has been done in 80s, and it has obtained more popularity now. So you might imagine that that below zero we have some kind of water, like a liquid, and above zero there is a gas, and then the particle is that thing in blue. It can occasionally, so it randomly goes above zero. When it is above zero in the gas, the particles of the gas, so the molecules, are very spread out, so they don't really interact with each other, or we can assume so. The interaction is small, and then they occasionally drop or penetrate the liquid, and when they are in the liquid, the distribution of the speed of the particle is concentrated in the upwards direction. So it goes upwards more than it goes downwards when it is below zero, so to say. Yeah, and the second example is an inline shop. So you might consider an inline shop production, an inline shop and your local production facilities. So you produce goods and you sell goods at the same time. You sell approximately the same number of goods you produce each day. Because if you don't do that, if you sell more than you produce, then you will be out of stock very soon. And if you produce more than you sell, then you will have to pay a lot for your stock, for storing your items. Yeah, so approximately you sell and produce about the same number of goods. So you might assume that the mean of your daily observations is 0, and then, but then sometimes you might have a lot of orders, and the orders might even make you go out of stock sometime. At that times, you consider not selling any more goods. You just produce goods, and these are those red lines. Plus, you might want to ask your friends or neighboring facilities to produce some goods for you, and these are also these red lines. I hope this kind of gives some motivation. Now, about the history, so the topic of functional limit theorems for random walks is quite long dated. It has been pioneered by Donsker, I think so. Then there were a lot of other authors who participated in this study. So, for example, Karlin and Shep, they considered a model of a simple random walk plus minus 1 with probability 1/2 and with local impurity at 0. So at 0 they have perturbation something like plus minus 1 with probability P and Q, and so they get a skew Brownian motion. Mindler-Zhizhin considered similar models and used semi-group theory to obtain their results. Pilipenko, I will talk about that a bit later. Iksanov and Pilipenko, they used martingale characterization to prove their results in a similar way that it is in Harris and Shep. And Gopin-Yer, a very recent result, there they consider a random walk which has different drivers above 0 and below 0. Both drivers are mean 0 with finite variance, but variances are different, and the obtained limit process is a skew Brownian motion. And the parameter of skewness is derived from the interplay of two distributions above and below 0. Okay, so also possible limit processes are sticky Brownian motion, and finally, I want to mention Brownian motion with jump x from 0. This is incomplete. This is fully incomplete, I would say, the list of historical references, but gives some notion of what happens. Now, the previous speaker has told already about slowly varying function. I will just reiterate some bits of it. So a slowly varying function is a function that varies slowly. That's the formula 1 holds. We say that a random variable has a regular varying tail if the tail decays like a polynomial function multiplied by a slowly varying function. And the reason to look at the slowly varying function is because there are a lot of generalized central limit theorems for this type of random variables. We can derive this type of theorems, and consecutively we can derive Donsker-like theorems. So I want to recall a theorem that states that if we have a positive random variables with an index of regularly varying with a regularly varying function with alpha in 0, 1, 0 and 1 excluding, then the scaled random walk driven by this random variable converges to an alpha stable subordinator without drift. We will need that. Now, two results. Let me denote W as to be a Brownian motion, and M is sign flipped random minimum. And now the theorem is the following. If we have an expectation of eta being a slowly varying function, after this is multiplied by indicate, then in the space of continuous functions, we have the convergence to reflected Brownian motion. I want to mention here that if eta has a regularly varying function with index in 1, 2, then this expectation is actually a slowly varying function. For alpha greater than 1 strictly, this is immediately seen as the expectation is finite, so the slowly varying function is just a constant. And when alpha is 1, this can be found in literature, and even the previous speaker cited this, not cited, but told about this. The second theorem is as follows. If the random variable has a slowly varying function with an index in 0, 1, then the scaled process would converge to this tricky W alpha process. So W alpha is a Brownian motion plus an alpha stable subordinator composition with an alpha stable subordinator inverse composition with a minus minimum of a Brownian motion. So this theorem is an evolution of Pilipenko Prykhodko 2014 paper. There they used Skorokhod reflection problem. They constructed a sequence of Skorokhod reflection problems and showed that they converge somewhere. So they used the continuity of these problems. And in our case, and it was possible due to the assumptions on Xi. So Xi was assumed to be bounded from below, and also the random walk was integer valued. We don't need those assumptions. Our methods rely on different results. Okay, and theorem 3 is about slowly varying tail. It's about when eta has a slowly varying tail, then there is no weak limit for a scaled sequential process. I want to comment a bit about the proofs of theorems. So theorem 1, we can give an equivalent definition for the process. It's like, so the process tilde as can be seen as a process as a random walk driven by Xi plus a random walk driven by eta. And then we want to show that it converges after scaling to a Brownian motion minus the minimum of the Brownian motion. And well, we know that this guy, if not without t, if without t, it would converge to a Brownian motion. So it gives some kind of way to tackle this problem. So this is more or less understandable. And the other guy is so due to the restrictions of the model, we found that minus minimum of Xi, so the random walk driven by Xi, it lies neatly between these two guys. So as long as we can show that they're close between each other and this tail is small, we derive the theorem. Yeah, and this theorem is closely connected to Pilipenko-Shevchenko 2015 paper. There they considered simple random walk plus minus 1 with probability 1/2, but at 0, they had an impurity which was something like you can jump wherever you want from 0, but the tail, and they had control over the tails of those jumps. And basically, they had the expectation of eta, like positive part and negative part, being a slowly varying function with different tails. And now the interplay between those tails gave like a skew, the skew Brownian motion. For us, it would be interesting to obtain a skew Brownian motion, but right now the model doesn't give us that kind of freedom. We can only reflect upwards. Yes. Now, as for the theorem 2, so we found that very conveniently that this process Rn, which bears close resemblance to the process that we need to prove that this is a limit. So we found that this process converges to this guy. Again, the first summon Xi of n. It is natural. It's Donsko's theorem. As for the second guy, it's less natural, so to say. So these guys, we have taken an approach from Struck and Andrey. They proved that if you have a random walk, one random walk, and the other one, which may be dependent on each other, and you look at, and then you look at a random walk that has goes from one level to another one, but then stays for a random amounts of times, like the other one. So yeah, one random walk, it controls the level, and the other one controls the timing. So they proved that this decomposition of those two would converge, and we used that theorem, and also and we only needed to prove that these two guys actually converge somewhere. Okay, so and lastly, we know that Rn converges somewhere. Now we need to derive something about S tilde, and we noted that S tilde is connected to Rn in this way, so it's time changed S tilde. As for the theorem 3, when alpha is 0, so we knew the theorem from Bingham-Goldie-Tegels, actually proved by Rogozin, that if we have, so consider a random walk as S eta, so it's driven by S eta, and consider a level epsilon square root of n. Now you look at the moment of the overjump of that level, and you look at the random variable that that eta that was at that that moment of the overjump, with which eta you overjump the level, and it's and it appears that that eta is very, very big. It's huge. Even divided by square root of n, it still converges to 0 to infinity. So if one could show that that this this moment of reaching that that level is happens quite fast, then one can show that the process blows up, and this is what we've done. Yeah, so coming to the conclusions, I suppose I'm good on timing. We analyzed all cases of distributions of penalizations where the tails are regularly varying, and as a bonus, we have some figures of the process that Brownian motion with the jump exit from 0. You see this jump. Yeah, that's it. Thank you for your attention.
Okay. Thank you very much. Some questions or comments, please.
Yeah, I'd like to comment on the case alpha equal to 0. That is when the tail of Xi is slowly varying. But in this case, it's very likely that you just need to use nonlinear normalization. What I mean, it's known.
I see.
Huh?
I see what you mean. I think you mean that we need to not the square root here, but something else.
No. For instance, it's known result for random walks that, of course, you cannot normalize Sn by anything to get a non-trivial limit. But if you make a non-linear transformation of your random walk, for instance, when your L is 1 over log x, then the correct normalization, if I remember correctly, log of Sn. So you can prove a weak convergence of logarithm of your random walk normalized by something. But if your slowly varying function is of different form, so this non-linear transformation depends heavily upon the form of your slowly varying function. And then it sounds very likely that you just need so you have to investigate not the process S tilde, but rather some process f of S tilde, where f somehow depends on your slowly varying function. You see what I mean?
Mm-hmm. Yeah, thank you. That's interesting.
But you know this, so there is this classical theory by Gnedenko and Kolmogorov, but it only treats convergence when alpha is between 0 and 2. Excluding 0. I mean, when the index of regular variation is positive, right? Mm-hmm. Then we obtain in the limit these stable Levy processes. Yeah, but there is a separate theory. It rests on somewhat different ideas. It covers the case when the tail of eta is slowly varying. Mm-hmm. So there in the limit, you obtain something like inverse process for the extremal process, if I remember correctly.
For renewal process, you will obtain inverse extremal process, and for random walk, just
extremal process, right? Thanks.
And correct normalization is if a tail is L, then 1 over L evaluated at Sn of t divided by n converges.
Yeah, something like that. Yeah, but there is a well-developed theory addressing this situation, and maybe it's not that well known as the classical theory of Gnedenko and Kolmogorov, yet there are a huge number of papers addressing this case, so I suggest that you just look into those papers.
Yeah, thank you very much.
Yeah, you're welcome.
Okay, thank you for the interesting comment. Maybe some other person want to say something?
Maybe I say a few words about this topic. It would be interesting to solve this problem with alpha equals 0 in two-dimensional case. Because even if the random walk is symmetric with probability 1/4, you go up, down, to the left and to the right, because a Brownian motion does not visit a fixed point, for example, 0. But if you have impurity in 0, but very strong, it is not known. Will we have a limit or not? Because if you jump far away, then a time of return is large too, and there will be some competition between time of return and large jump. And so it is known that if the exit from 0 has regularly varying tails with alpha greater than 0, then the limit is just Brownian, just two-dimensional Brownian motion. So this impurity does not affect the limit. But the general case is not clear. And it's interesting to generalize this, this type of problem for random walk that behaves as that belongs to domain of attraction of alpha stable low above 0. Or for example, you may have jumps that belong to domain of attraction of alpha stable low above, below, and some impurity, some additional term when you cross 0. Probably limits of some scaling limits of such sequences may be called as skew alpha stable Levy process, but this is for future.
Yeah, thank you.
Okay, thank you very much. And we have to end the discussion because of the next talk. Next talk will be delivered by Hennadii Navrotskiy from Kyiv Polytechnic Institute, and name of the talk is Asymptotics of Vasiliev invariants of stochastic braids under my supervision. Okay, Hennadii, you can translate your screen, please.
So, yes, so the topic of this study is asymptotics of the logical invariance of small braids, and the goal of the study is to investigate the time asymptotic of such variants of braids which are composed from trajectories of solutions of differential equations with smooth non-divergent vector fields. So first let's describe the what the smooth braid is. A braid of n strands is a set of n continuous mappings from the z1 to zn from the segment of 0, 1 to C, where C is a space of complex numbers. And for any t from 0 to 1 and for any I equal to g, there the ZE isn't equal to G. So they're not crossing. And such functions also can be presented as a set of continuous not crossing curves in R cube, which are drawn between the planes T0 and T equal 1. Yes. So the simplest example of such braid is just a set curves which go from some subset of initial points x1 to xn and end in these points in t equal 1. Yes. And the main objective of conservation invariance is to distinguish between non-isotopic braids So they take the same values on braids which are public, and if the system of braid invariants is complete, then for any two non-topic braids, there exists an invariant in the system which takes on different values on these two braids. Yes, and for small braids there is such system by Maxim Kontsevich and called the Kontsevich invariants. Yes. So let's describe such invariants. So that invariants we need to build a new objects such as diagrams which are connected to the A to the matrix of the certain form. So if the n is a number of strands in a braid, then we should build this braid following matrix with n strings and m rows. Yes. So for each matrix we should build some diagram which consists of n vertical lines that corresponds to the braid strands and m horizontal segments that correspond to the rows matrix A. Yes. And each horizontal segment corresponding to this row connects the segments AE1 and AE2, and those segments such that for E this and D, the each segment is above the E. So and then we should build a coordinate space by the following relations. So the matrix A and A prime will such form, so only two strings are changed. Then the values of the diagram, the dA is equal to the dAi. And the next relation is for T relations, which is for more complicated matrix, such as if we have two matrix with in which some strings there are repeated elements like A, B, and BC, then still there are values on them. Diagrams corresponding to this matrix are not changing. Yes, and then the our space of diagrams for M is quotient of space V by the subspace U, where our space V is the space of all our linear combinations of diagrams V, and its linear span of elements with the following forms, which have the form described earlier. Yes. Then by these diagrams we could build Yes. So we build diagrams by the matrix. So there is a first string of matrix which corresponds to our first horizontal segment, and the second line which corresponds to the lower horizontal segment. Yes. And the Kontsevich integral of the m of the order m is for the smooth braid built by such diagrams by the following equation. So it's the sum of n a in AMN, where AMN is the space of diagrams for the m, and n is the number of strings of a braid. Yes, and the braid composed of so our particular topic is the braids, which are composed of trajectories generated from the smooth non-divergent vector field in some domain C, the space of complex numbers, and such the braids, the trajectories are built as a shift along the solutions of these equations with fixed initial points. Yes, and as we want to investigate the convergence of such functions, topological invariants of our braids, we need to use the ergodic theorem, which states that for such measure preserving flows, there exists a limit which equals to expectations of f to e, where e is the sigma algebra of subspaces of S and relative to the form G. Yes. And in case of form, such limits equals to the integral on S. And by applying this theorem to our traversal angle phi, and with for the braid, which consists from only two strands, which goes out from the points x1, x2, we have that there exists a limit of the ratio of this traversal angle to t, and it does depend from the initial positions x1, x2, and then there exists a limit of the ratio of to t to the power m, mt for almost all with respect to measure mu initial points e from S, where m of t is Kontsevich integral of order m, and lambda is the limit for only one such braid, for only two such strands. So and as each Vasiliev Kontsevich invariant is just the linear combination of such integrals, then there exists a limit for all of the Kontsevich invariants of this braid as the t approaches infinity. So for the proof, we want to use the following lemma because we have by the conditions mentioned that there exists a limit for just two strands, and we want to prove the theorem for any set of strands. Then we need to take the multiplication of such functions and look at the ratio to t at the to the power of n. Yes, and then we would have divided. We will have just the multiplication of the limits lambda into x divided by the factorial. It could be solved by using the method of systematic inductions. And yes, so first we will, it could be proof for just the two strands, and then for the n. Yes, and applying our previous lemma and Behaviour-Hinch ergodic theorem, we could conclude that for all such functions, there exists a limit when t goes to infinity, and is the same for almost all with respect of the measure mu for start points x if S where S is our compact domain in the space of complex numbers. Yes. So that's all. Thank you.
Thank you. Maybe some questions, comments?
Would you please recall us properties of this dynamical system xi of t?
No, it's our ergodic phase field, and it is well, it is not necessarily ergodic, but it is necessary measure preserving.
And could you please show us some examples, maybe?
Yes, so, well, the easiest example is a movement. Well, it's a shift on the circle circle or by some angle alpha and such. And if our measure is well just a Lebesgue measure on the such circle, then it would be a measure preserved.
And is it possible to prove such theorem if XIT are random processes, say solutions of some stochastic differential equations?
I think that Hennadii don't know exactly what is stochastic differential. But let me comment exactly. My comment was supposed about your question, because some of the participants of our seminar remember results of Vasily Kuznetsov also about the asymptotic behavior of the rotation number of strength in the braid, which is obtained from the stochastic flow. What happened, let me recall your results. The first one was Wigner, and Wigner's law for one planar Brownian motion says that the rotation number around some fixed point, which is not starting point, is proportional in weak sense to the square root of logarithm, and the weak limit is Cauchy distribution. Then the same was proved for independent family of Brownian motion, that their pairwise rotation numbers also must be normalized by square root of logarithm t and have the same weak limit Cauchy distribution, moreover independent Cauchy distributions. After this, Vasily Kuznetsov began to study the solution to stochastic flows. And he was able to prove the same statement with normalization square root of logarithm t for rotation numbers in the Brownian stochastic flow, where the greatest Lyapunov exponent is equal to 0. It means that this is not stability case. In this case, the solution to our stochastic differential equation, if we want to describe our flow by stochastic differential equation, goes one apart from another as far as we want. We, in this work of Hennadii, we were tried to consider opposite case, where we have stability. And from the theorem which he presents, we can see that in ergodic case, we have a very different situation. All Kontsevich invariants have good normalization, and this normalization is proportional to the, say, roughly speaking, power of invariance, Km, T, or in M power. I think that in case of Brownian flow, we will continue work, because in my opinion, the same statement can be obtained for Brownian flow with the greatest Lyapunov exponent equal to 0 for say oldest Kontsevich invariant, but still it is open question. The aim of the talk was to consider ergodic case of for Kontsevich invariants for dynamical system. Okay, so now we have a break for half an hour, and next talk will start at 4:30. So we can
4:30 Kyiv time.
Yes, just almost half an hour, and everybody can make coffee, can leave conference, or just remains to be here. At least in my case, I have to prepare coffee, so I will be back after some minutes. Okay.